from computing architecture laboratory. Hello everyone, my name is from Computing Architecture Laboratory. So today I will present for my master thesis defense. My presentation has the title is High Performance SHA-256 Accelerator for Society 5.0. And thank you everyone for coming today. Let's take a look through my presentation. Firstly, I will introduce about the Society 5.0 and some application of the SHA in the Society 5.0. Next, I will overview the background, including the SHA-256 and the related work. The related work had some problems, so based on this problem, we proposed the architecture with the 3 solutions. And I will show the experimental result on the next part, and the final part is conclusion. In Information Society 4.0, they focus on centralized system, but in the Society 5.0, they focus on the decentralized system and data sharing. So a huge amount of data will be transferred between the physical space and the cyberspace. So the data security is very important in Society 5.0. And the SHA is used for the data security. The SHA works by transforming the data, the black text to the hash value using the hash function, and basically it is impossible to transform the hash value back to the original data. And there are 4 generations of the SHA family, and in our case we focus on the SHA-2 and especially the SHA-256. And I want to introduce the application of the SHA in Society 5.0. The first is the digital signature algorithm and the hash-based message authentication. So they provide the message authentication and the integrity checking for the data inside the Society 5.0. And the SHA is main component in the DSA and the SMAS. Another application for the data sharing in either decentralized system, and the SHA used for verify the data transfer between its nodes. And the most popular decentralized system is the Bitcoin network, and Bitcoin consumes a huge amount of electricity. So then we need an accelerator that is high throughput, reasonable power consuming, and has the scalability. Next, I will explain more detail about the SHA-256. Basically, it takes the input with 512 bits and produce the output with the 256 bits. And the computation process including 2 main steps. The first step is the emit step. It needs to calculate 2 functions and repeat in 48 loops. And the MC process, it need to calculate several small functions and repeat in 64 loops. So we can summarize some characteristics of the SHA-256, like they use more than 2,000 simple operators for compute 1 loop, and to produce a hash value, they need to it needs to repeat in 64 loops. And the third is the output of the current loop will be the input for the next loop. So next I will overview some related work. So the first, they use the feedback line. This means they use only 1 PE and repeat in 64 loops to produce a hash, and it leads to the low throughput. And also they they store the output to the external memory in every hash, and it leads to the low latency transfer data to the external memory. Try to solve the problem, we decide to highlight RAU. And the second one, they use the optimized SHA-256 algorithm, and they still store the output to the internal memory every hash, and also still have the problem with the low latency transfer data to the external memory. And with this problem, we try to design the local memory inside the PE. And the third, they use the highlight technique for the loop level. It means that they use many computation units inside the PE to reduce the loop. So, but they just design for the single core. So it's okay. We try to solve that problem by design the multi-core. And all of them just focus on the computation core and do not care about the data transfer in the system level. So we try to design the accelerator that suitable when implementing on the SOC level. And this is the overview of our architecture. So the first solution is the pipeline RAU. Let's look at the algorithm. So the final target is the hash value. And we need to calculate the T1 and T2. So in this T1, we need to calculate the WG, it means the ME. And to save the time, we calculate the ME, we compute all the function inside the ME with some function in the MC at the same time. And so after 4 clock cycle, so the RU can finish one loop. And we try to design the RU pipeline with 4 data flow. So the second solution is the local memory. To match with the speed of the RU, so the data need to available when the RU required. And however, the bus connected between the accelerator and the external memory always limited. So then we try to design the multiple local memory inside the PE, and it will be used for temporarily store the input data inside the PE, and the RU can always the input data always available before the RU start, and we can exploit the higher performance of the RU. And the next solution is the multi-P accelerator. So we have many kind of applications and many kind of platforms. So our accelerator can change the number of the PE by the preconfig parameter depending on the requirement of the application. Our accelerator including an array of the PE and has the assign bus interface and connect with the external memory through the global controller. And combine 3 solutions, our accelerator is suitable with, when implementing on the SOC level. And this is the hardware implementation of the pipeline RAU. We have the ME here. The input of the ME is the input data. And we have the MC here. The input of the MC is the initial value. And after 2 clock, the output of the ME will be available, and it will be stored to the local memory. And at the same time, it also will be transferred to the MC for the next calculation state. And after 4 clock, the RU finished one loop, and the result will be feedback to the input to continue computing into the 64 loop. And only the final value will be transferred to the local memory. And we design the RU with 4 parallel states, so that this RU can compute 4 data clock in for parallel clock cycle. And this is the hardware implementation of the PE. And the PE had the IOU and two local memory. The left side is the WRAM. The WRAM will be used for the ME, and the right side is the SRAM will be used for the MC. And the WRAM store the input data and the reduced data for every loop. And the SRAM store the initial and the final output. So by this way, multiple input data can be stored in the WRAM, and when the LU finish computing every input data, the final output stored in SRAM will be transferred to the external memory. So by this way, we can reduce the latency time to access the external memory. The first solution is the multi-PE accelerator, and the multi-PE accelerator including array of the PE, and it can be controlled by the host CPU in the processing system, and to control the every PE, we designed the control register. The control register had 20 bits and had two modes. The first mode is for the transmission data, and the second mode is the configuration. And we have 6 bits to control 64 PE, and the remaining bit will be used for the mapping the data to its slot inside the local memory. And this is the timing chart. The timing chart shows the operation way of the every PE. Our accelerator starts with the PE 0, and when the PE 0 change to the execution mode, the PE1 starts to receive the data from the input data from the outside bus, and so on. And by this way, every PE can share the hardware resource of the outside bus, and we can increase the throughput of our accelerator. And next is the experimental result on FPGA. So to be the most fair, we try to compare the IOU with the IOU and the PE with the PE. We compare in several FPGA platforms from the version 2 to the version 6. And this is the latency of the result. And as you can see, our architecture can get smaller latency and in case of throughput. So because we use the pilot state and we parallel computation the ME and the MC, so we can get the high throughput. In terms of the version 2 platform, we achieve more than 2 times higher than the design. And so in the version 2, version 4, we also achieve more than 1.4 times, and it is the same with the version 5 and version 6. And our accelerator requires the large hardware resource, but in case of the trade-off, our aerial efficiency still get the good value compared with the good result in the version 2 platform, and compared with the version 4, a good result with the version 4, our accelerator achieved more than 1.2 times, and it is the same with the result on the version 6. And this is the experimental result on the FPGA of the PE. Some research they use the full PE, but some they don't put the local memory inside the PE, so we try to compare it with them. And but the version 2, so we get achieve a higher more than 3 times compared with the result on the version E, and in the version 2 we get higher than 4 times, and compared with the related work 4 we get the higher than 7 times, and compared with the related work 3 we get the higher 2 times. And this is the conclusion. So many work try to improve the throughput of the computation core, but they do not care about the data transfer in the system level. And our accelerator try to solve that problem by designing accelerator suitable with the SOC level. And our accelerator had 3 solutions: the finite IOU, the local memory, and the multi-P accelerator. So the results show that our accelerator had the throughput and the hardware efficiency are outstanding with the previous work. And this is the publication until now. And this is some related work I used in this presentation, and that's all of my presentation.